Here is the dreaded topic, no, not dreaded, but the promised topic that we've been talking about in the previous section. Logarithmic functions, this is section 4.2. Just something to keep in mind, which we'll point out later, but this is the idea. They're inverses of exponential functions. So we studied exponential functions in the previous section, section 4.1. Now we're going to study their opposite, or their inverse. And there are actually applications in real life of logarithmic functions. Like here, the one they're talking about is the loudness of a sound level is measured in decibels. Decibel levels range from 0, which is a barely audible sound, to 160, a sound resulting in a ruptured eardrum. We'll see that decibels can be modeled by a logarithmic function. You probably see that in the homework somewhere, a topic of this section. So, what's the definition of a logarithm, and how do we write them out? You know, what do they look like? So here, this is the definition. It says let b be greater than 0, so it has to be a positive number. And also, I don't know how this happened. I'm not sure if your guys' pictures or your notes look like this, but b should not be equal to 1. That should be a not equal to sign, sorry. Then n is the logarithm of m to the base b, written da-da-da-da-da. Okay, that looks really blurry, but what it says is log base b of m equals n. Pretty much that means that b to the n power equals m. It's just another way of saying it, and it's really confusing, but it's definitely worth, I'd say the most important thing about logarithms is that you want to memorize this transition here. This guy. So if you see this log base b of m equals n, you should be able to write it like this. That's the first thing we'll practice, excuse me, in this section, but it's really, 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 really important. So we'll kind of practice that. So notice that b, the little b that they have down there, let me see, da-da-da. This little guy, they call it the base of the log. It's just like a little subscript. It's a good name for it, b for base, because it's the base of the exponential as well. So that's a good thing to remember. The little number in the log, the one that's kind of down low and it's really small, that's going to be the base of the exponential. And then the number that's on the other side of the equal sign, here it's n, I guess a number or a letter, whatever, is the exponent. So it's b to the n power. And then the argument, they call this guy the argument, the number that's kind of the larger number in the log is what the exponential is equal to. So it might not be a bad idea to kind of write down the names of these parts. We've got the little number is called the base, which is only because in an exponential function that's the base. And then the m here is called the argument. Argument. And then n, that's on the other side of the equation, ends up being the exponent, we call it, because if you rewrite it as an exponential, like we see here, it ends up being the exponent of the exponential. So that might help us. Let me see, I'm going to take what they gave us in this first example, log base b of 25 equals 2, and rewrite it. So we said that, let me see, if as long as I remember the names of everything, that should help me. B is the base. And then we said this guy, the number or letter that's inside the log, other than the little number, is called the argument. And then the number that's on the other side of the equation is the exponent. So that should kind of help me. Base b, that should be the thing being raised to the power, and then obviously the exponent is the power. And then I guess through process of elimination, the last thing left should be what this is equal to, 25. And that's all they wanted us to do. They don't really want us to solve an equation, they just want us to practice rewriting a log as an exponential. Let's try this other one. We've got log base 6 of 216 equals y. So we gotta just label, either in your mind or actually writing it out, it helps to label the parts. The little guy, 6 is the base, so I know that's what's being raised to the power. The big number is the argument, we call it, argument. That's kind of, I usually fill that in last because it's hardest to remember where that goes. Y in this case, the number that's on the other side of the equation is the exponent. So I know that guy is definitely going to be what the base is being raised to, what power. And then, like we said before, by process of elimination, the number I haven't used yet, or the letter I haven't used yet, must be what this is equal to. And that's what they wanted. Like I said, they just want us to rewrite this guy. This, what I just wrote, I'm highlighting right now, is the same exact, it means the same thing as what they wrote. Log base 6 of 216 equals y. That's the same as saying 6 to the y power equals 216. just like a rephrasing of it in a different way. And sometimes it'll suit us to have it in one form, and sometimes it'll suit us to have it in the other. It kind of depends. So okay, now in this problem, in objective 2, they want us to go backwards. So they're giving us the exponential and wanting us to go to the log, which I think is harder. So I'm going to rewrite kind of what we had before. It was log base b of m equals n. And it kind of helps me to remember that the b we called the base. Okay, that helps me. Base. This guy was the argument. And this guy is the exponent. And that helps me remember where everything goes, because obviously here 2 is the base. Because base, we said base is what's being raised to the power in the previous section. 5 is the exponent. So I kind of know where those go, just following along with the model of the log. It's log base, okay. The little number is the base, which is 2 from the exponential function. The argument, I'm not sure yet, but on the other side of the equal sign should be the exponent, 5. And then, like I said, through process of elimination, the thing I haven't used yet, this x, should go here. This is really hard. Yeah, it's really weird and hard to remember, but if you get this down, then logs won't be so bad. It's definitely worth memorizing this whole transition. Let's try another one. It's like this guy, 7 is the base, which should be the little number in log, log, and then little number, something equals something. The exponent is what's supposed to go on the other side of the equation. So I'll put that on the other side. And then by process of elimination, the number that's on the other side of the equation in the exponential function should be the argument in the log function. So it's just like a rearrangement of 3 numbers or 3 letters that you have to memorize to do well in this section. All right, so now that we've kind of memorized that rearrangement, because that'll really help later in a coming section, now we're going to just evaluate logs. Like if you have all numbers inside the log, what do you do? So it says log base b of m, it represents the exponent to which b must be raised in order to obtain m. So I think at first that's kind of hard to wrap my mind around. I'm like, what the hell are they saying? But if we look at this guy, for example, evaluate log base 2 of 32. This represents, like it says, okay, this represents the exponent to which the little number b, which is 2, must be raised in order to obtain m, or 32. So in other words, 2 to what power is 32? And that kind of shows the rearrangement, I guess. If I said, log base 2 of 32 is what? Well, if I were to just rearrange that, like we've just learned in the previous objective, it would look like 2 to the question mark power equals 32. And then you can just kind of guess, 2 to what power is 32? Let's see, 2 to the first power is 2, that's not right. 2 to the second power is 4, 2 to the third power is 8, 2 to the fourth power is 16, 2 to the fifth power is 32, so the answer is 5. And that's because 2 to the fifth power is 32. So if someone asked you, what is log base 2 of 32, you'd say it's 5. Like I said, yeah, it's like it says, a log is like an exponent. It's saying there was an exponent that someone, I guess it's like someone raised this number to a power, 2 to some power, and they got 32. Your job is to go figure out what that mystery exponent was that they raised it to. So try to do the same thing here. This guy, evaluate 4, let's see, log base 4 of 16 equals whatever. That means even if, like you said, if you already memorized the rearrangement, that kind of helps. This is asking 4 to what power is 16? Well, we know that that power is 2. 4 squared is 16 because, so the answer is 2. 4 squared is 16, all right. 2 is all I need. That's the only thing I need to say. And here's another one. Now these next two, they kind of test you on your, what's it called? On your the exponent rules. So this first one, log base 5 of 1/5. That one we should know because we've written down the corresponding exponent rule earlier. But then the one after that we might not know. I'm going to create an exponent rule for that. But anyway, actually, it's kind of misleading to write the exponent rule on a side and this guy in the same color because we don't need that exponent rule for this one. I'm going to write it in a different color. They're asking for a log base 5 of 1/5. So this says 5 to what power is 1/5? And we talked about this earlier. What power do you raise a whole number to get a fraction? It's a -1. Remember, we did that earlier when we were, actually in the previous section, when we were graphing exponential functions. If we substitute a negative power in, all of a sudden we got a fraction from it. So that's because 5 to the -1 power is 1/5. So that was, yeah, an exponent rule that we saw in the previous section. So it's not really anything new, but I think for this very last one, log base 36 of 6, this guy here, we're going to need a new exponent rule that you might have seen in a previous class, but you haven't seen it in a while maybe. An exponent rule, if you have some base to a fraction power, like 1 over n or something like that, that means you're actually taking a root of that guy. So for example, if I said I want to do, I don't know, 100 to the, no, not 100, how about 27 to the 1/3 power. That really means the third root or the cube root of 27, which is 3. So I think that'll help us with this guy, this last one. This says 36 to some power that I don't know was 6. Well, usually when you raise something to a power, the number gets bigger, you know, like 2 to the first power, 2 to the second power, 2 to the third power. But I'm supposed to raise 36 to some power and it gets smaller. Well, I guess what I'm thinking is, actually what I could do to 36 is square root it and I'd get 6. So the power I want is a 1/2 power, because as we just reviewed, a half power represents a square root. So the answer to this guy is a half. Or I guess 0.5 if you want to write 0.5. So logs, they're kind of weird, but yeah, you kind of get the hang of them the more problems you do, so that's the good part. Alright, let's try these next two. And in objective 4, we're going to use basic logarithmic properties to solve these guys. But I think what we can do is once we solve them, I think we can come up with a rule that'll help us later. Like this one, it says, okay, evaluate log base 7 of 7 to the 8th. So it's like 7 is your base, and 7 to the 8th is your argument. So this is saying 7 to some power, I don't know what it is, equals the argument 7 to the 8th. Well, that's kind of more clear if I write it like that. 7 to what power is 7 to the 8th power? Well, I think it'd have to be 8, right? So it's just more like, you're just equating exponents kind of. Whatever the hell this is, this exponent should be equal to this exponent. So 8, that would be it. And I think now that we see the answer, we can make a rule out of it, because the 7 and the 8 weren't really unique, you know what I mean? This problem could have had anything where the 7 was and anything where the 8 was. I'm going to come up with a new rule, log base b of b to the m. So if it looks anything like that, where your argument has a base that matches the base of the log, it's kind of like the bases cancel, you know what I mean? Sort of. Bases cancel. So that's a rule, and that might help us with some future problems, maybe some problems in your homework, but that's a rule we can come up with now that we've kind of seen what happens. And I think we can come up with another rule for this guy. This is log base 4 of 1. There's a period at the end of this sentence, but it looks like it's a decimal point, sorry. This is saying 4 to what power is 1? Well, if you remember one of those exponent rules from the previous section, we said anything to the 0 power is 1. So the answer is 0 because 4 to the 0 power is 1. And then, kind of like in the previous one we did, the 4 isn't really unique, you know, that base 4 could have been anything. So I can come up with the rule, log base anything b with 1 as an argument is going to be 0. Because this is asking b to what power is 1? Well, b could be anything. You raise it to the 0 power, you're going to get 1. So I guess basically as long as your argument is 1, the answer is going to be a 0 no matter what the base is. Alright, now we can talk about graphing logarithmic functions. So, like we mentioned before, what happened to this guy? I should say log base b of x, sorry. I don't know where that guy went. Okay, it says note f of x equals b to the x, so the exponential function b to the x, and the logarithmic function log x, so this is exponential with base b, and this is a logarithm base b. base b. They're inverse functions. I kind of talked about that earlier, but that comes in handy in this part because we know how those, remember we talked about it before in chapter 2, inverse functions are, their graphs are reflections of each other across the line y equals x. Let me write that down. Recall the graphs of inverse functions are reflections of each other, I guess. Reflections across the line y equals x. So all that to say, to graph a log, graph its exponential inverse. Then reflect across the line y equals x. So this kind of helps because remember in the previous section we had to figure out how to graph exponential functions. We had to start at the drawing board. We had to just plug in x values and see what happens. And we would have to do that for logs, but we're just going to take advantage of the fact that we know how inverse functions graphs look. So I'm going to go ahead and get ready. I'm going to draw the line y equals x. I don't know if you remember that diagonal line from chapter 2. And then I'll graph, let's see, I'm going to color code it kind of, let's see. Let's say we have, I'll say that the exponential guy is an orange function. So from the previous section we found that since the base is 3, which is greater than 1, that means that graph's going to increase from left to right. So it's going to be close to the x-axis and then it's going to slowly go up like this. Something like that. But now if I want to graph the log, and that log is associated with this exponential because it has the same base, notice. I don't know, pink and orange are too similar, huh? Let's try, what other color? Purple? Purple's good, huh? Okay. Yeah. So since the base of the log and the base of the exponential are the same, then they're inverse functions. I'm just going to reflect the orange, I guess, across the line y equals x, and that should be my graph. So if I try to reflect this guy, I think it's going to be, instead of getting closer to the x-axis in the negative direction, it's going to be getting closer to the y-axis in the negative direction, and then increasing kind of, instead of upward, it's to the right. So those are, what's it called? Those are inverse functions graphs. I forgot to label it, sorry. This is f of x, the 3 to the x guy, and then g of x, the inverse guy, should be log base 3 of x. So yeah, don't worry about necessarily memorizing the graphs of logs. I guess you could if you want to, but there's no need because we've already memorized exponential functions graphs, so we don't really need to memorize these guys. And then part B here is similar, except the base of this exponential is a half. So since b is a half, which is less than 1, this is going to be one of those decreasing from left to right exponential functions. So it's kind of, it's close to the x-axis on the right side of the y-axis, and it shoots up on the left side instead of the other way around. So that's the graph, of f of x equals 1/2 to the x. We saw that in the previous section. And now I'm going to draw the line y equals x, just so I know what to reflect across. Oops. Let's see, yeah, there we go. Y equals x looks like this. Y equals x. There he is. Now I want to reflect the orange graph across that line. But this is going to be kind of hard, so I gotta kind of think about it. Sometimes, like I said before, it helps me to think of one portion of it. I'm just going to picture the portion that's below the line y equals x. Let me highlight it here. I'm going to reflect this part first. If that guy reflects across that diagonal line, I think it's going to be, instead of approaching the x-axis, it'll approach the y-axis. So it'll look like this. Something like that. Okay, now we'll focus on the other part of it. Now I have to reflect this part. And kind of like in the previous one, instead of shooting upward, it's going to shoot off to the right. But it's going to be continuing from the purple graph, so it'll go something like this-ish. So those kind of look like reflections across that line, g of x, log base 1/2 x. There they are. So yeah, no need to memorize the graphs of logs. It's kind of, I don't know, kind of silly, I guess. All right, and then, at this point, we've seen how to find the domain of any function that we're familiar with so far. We saw that in Chapter 2, but in Chapter 2, we didn't know about logarithmic functions. So now we kind of have to come up with a way to figure out the domain of a logarithmic function. And it's not so bad. It's kind of like a square root function, if you remember those guys, or any even root function. Here we have it highlighted. To find the domain of a logarithmic function, we're going to set the argument, which is what's inside of the logarithm, greater than 0, and solve for x. This is because we can't have negative numbers or 0 inside the logarithm. So for 6a here, let's try that. It doesn't, for the domain anyway, it doesn't matter what the base is. 4 is not going to have any bearing on this problem when I find the domain. I'm just taking the argument, which in this case is x minus 5, the thing inside the log, and I'm setting it greater than 0 and solving for x. So I would only need to move the 5 over. So it looks like x greater than 5 is the domain, but interval notation would have that written from 5 to infinity with parentheses because there's no or equal to. Alright, and then we'll try that again in the next 6b here, just to kind of really nail it down. I just set what's inside the log, the argument, greater than 0. And then I'll solve it. So maybe I'll move the 2 over. Negative x is greater than 2, and now I'll divide by negative 1. But don't forget, when you take an inequality and you multiply or divide both sides by a negative number, I have to flip that inequality now. So don't forget, it was started out as a greater than, which is the way all the domains of log functions should start, but it's switched the other way because I divided or multiplied by a negative number. So x is less than 2, which in interval notation would be negative infinity to 2. And I think this last one is a little more complicated. It'll kind of involve something that we've seen a few sections back. Sorry, I don't know how this guy got messed up. It's supposed to be like this. This x squared was supposed to be part of the same line. They want us to find the domain of this guy. So just like the previous two, the base, in this case 7, doesn't matter. It's only what's inside the root that matters. Or sorry, inside the log that matters, the argument. I'm going to solve this guy. And this guy, since this is not something where I can just get x by itself, this is actually a polynomial inequality that I've seen in a previous section. Oops. Polynomial inequality. So here's another example of where you might use polynomial inequalities in other areas. So that was the previous, or 2 sections back, 3.6 I believe it was. Remember there were a bunch of steps. The first step was I have to take that inequality and make it an equal sign and solve for x. So if I solve that for x, I can get the x squared on one side, the 16 on the other, and then square root both sides. Let's see, square root, just don't forget the plus or minus, so it should be plus or minus 4 is x. Alright. So the numbers I found were 4 and negative 4. We're going to put those on a number line, that was the second step. And then choose test values. So, okay, now I'm going to test something less than negative 4, how about negative 5? Something between negative 4 and 4, how about 0? And then how about something between, or sorry, something larger than 4, I'll say 5. And we're supposed to test it in the original inequality, which was here. 16 minus x squared is greater than 0. I'm going to plug it in there. 16 minus x squared greater than 0. 16 minus x squared. 16 minus x squared. Alright, let's try to plug it into the leftmost one first. If I put a negative 5 there, let's see what happens. Negative 5. 16 minus, okay, negative 5 squared is 25. And no, those negatives don't cancel because one of them is inside of a square. The square takes precedent first. I have to square the negative along with the 5 before I consider the negative in the front of the parentheses. 16 minus 25 is negative 9. That's not greater than 0, false. Okay, how about the next one? Now I'm substituting 0 in. 16 minus 0 squared is 0. 16 minus 0 is 0. And 16 is greater than 0, so it's true for the middle guy. The last one, what if I put a 5 in? 5 squared. I think I'm going to get the same thing I did on the leftmost one. 16 minus 25 is 9. Sorry, negative 9. Negative 9 is not greater than 0. That's false. So it looks like the middle interval is the one I want. Negative 4 to 4. There it is. So that kind of shows even logarithms and polynomials are connected. All right, interesting. Now we're going to look at some applications of logs, and that'll be our last objective, and then we'll see more logs in the next section. But I think from here, pretty much everything is just going to be we're plugging things in and using our calculators. So I feel like I've used my brain enough in this section. Now it's all about calculators. So number 7a, it says, the percentage of adult height attained by a boy who is X years old can be modeled by this crazy guy right here. Holy crap, that's a serious function. Where X represents the boy's age and f of X represents the percentage of his adult height. Okay, so I guess, you know, when X is like 20, for example, he's an adult, or I don't know, 21. Is 21 an adult, or 18? Whatever. If X is 21, I'm imagining it's about 100% of your height, because you're probably not going to grow much after 21, right? So it's going to be, our answers in f of X are going to be somewhere between 0 and 100. But what they ask is, approximately what percentage of his adult height has a boy attained by age 10? So pretty much this is just an excuse for us to plug 10 into this function. 29 plus, I'm just now copying the function, 29 plus 48.8 log of 10 plus 1. And you actually have a log button on your calculator. So you should see a LOG button. So when I type this in, I'm going to type in on my calculator 29 plus 48.8 times, I think that's how my multiply button looks. Is it? No, it's just times. And then there's a LOG button. And then it'll have parentheses, I'll put 11 because these guys add up to 11. So let's see, and I can do that all at once, it's not too bad. 29 plus 48.8 times log, where's log? There it is. Of 11 equals, and I get about, 79.8%. They didn't really tell me where to round, but I guess that's good. So by age 10, a boy is 79.8% of his adult height, or maybe 80%, I guess. That sounds about right, I guess, huh? You're pretty tall when you're 10 years old relative to how tall you're going to be as an adult. Alright, let's try this next one. This sounds interesting. So it sounds similar, but it's for a girl, huh? The percentage of adult height attained by a girl who is X years old can be modeled by... It looks a little different, but it's got the same feel, I guess. Where X represents the girl's age and f of X represents the percentage of her adult height. Approximately what percentage of her adult height has a girl reached by age 13? Alright, let's plug that in. F of 13, and I can probably just type this in my calculator, you know, in a similar way to the previous one. 13 minus 4. So I'll be typing in 62 plus 35 times the log button 9, because 13 minus 4 is 9. Let's see what we get. 62 plus 35 log of 9. I get about 95, wow, 0.4%. So pretty much by age 13, a girl's almost done growing. She doesn't have a whole lot left. It's like maybe 5% of her height is left to be grown, I guess. Is that the right word? That's interesting. Now these last two application problems, they involve what we call a natural log, which involves the letter E. If you remember, E was like, what was it? It was the number 2.718, and went on and on and on. Because I think we said that number occurs a lot in nature. It's kind of like population growth and a lot of things like that. You see E a lot of times. So I think that's why they call it the natural logarithm. So you probably see a button on your calculator that looks like ln. If you have some kind of scientific calculator, that's what they mean by it. It's actually a log in disguise. It doesn't look like it, but it's a log. Y equals ln. So if someone says y equals ln x, that really means y equals log with a base e of x. So yeah, if you ever see ln, just think base e. Okay, not that it matters when you're using a calculator, because your calculator obviously has the ln button, so you don't really need to know the base. It's just for future sections that's good to know. They want us to find the domain of this guy. Well, the good news is the domain is the same. Same domain. You know, you find it the same way, I guess is what I mean. So I'm going to do like we did before, set what's inside the log or the argument greater than 0, and then solve for x. So I'm going to subtract the 4 to the other side. Alright, negative x is greater than negative 4. And then I'll divide by negative 1. Let's see. And then that, like we've seen before, that will force the inequality to face the other way. Now it's x less than 4, positive 4. So x less than 4 means our interval is negative infinity to 4. That would be the guy. Good stuff. All right, so far so good. And I think this last one is going to be, similar to the applications we just saw. It's just that when I go to type stuff in my calculator, I'm going to have to press the ln button instead of the log button. That's the only thing, because, yeah, they have since they have an ln here instead of a log. But otherwise, I think this should be really similar to the previous applications problems. Use the ln button on the calculator instead of the log button. Yeah, anyway. So what does this function represent? Models the temperature increase f of x in an enclosed vehicle after x minutes when the outside air temperature is between 72 and 96. Use the function to find the temperature increase to the nearest degree after 30 minutes. Okay. So it's not like when we substitute 30 in there, which is what we're going to do, f of 30, it's not going to tell me the temperature inside the car. It's going to tell me how much it's increased since the time started. So that's kind of interesting. Okay. It's supposed to be 13.4 ln of x, but my x is 30, and then minus 11.6. Let's see. Yeah, we substituted 30 in. So on my calculator, I'm going to type 13.4 and then, multiplied by, and then there's an ln button. And usually when you press the ln button, it should open parentheses. 30. Make sure, though, you close the parentheses. Because sometimes if you don't, it'll think that you're subtracting 11.6 and it's still inside the log. So you definitely want to close the parentheses if it opened any when you press the ln button. Okay, I'm going to type that in and see what happens. 13.4 times ln, okay, and I'll put a 30 in there, but I'm going to close the parentheses and then minus 11.6. And I'm getting, ooh, really? 33.98. Wow, that's a lot. So I guess that's why, it's such a serious thing. You can't leave your dogs or especially your kids. Come on, what the hell? You can't leave your dogs or your kids in the car while you go to the grocery store because you think, I don't know, 15, 20 minutes isn't that long, but the temperature increases by 33.98 degrees, and I guess that's if the temperature in the car is anywhere between, or temperature outside, sorry, is anywhere between 72 and 96. That's a big difference. So if it's 96 outside, 30 minutes later you add 30 degrees to that. Oh god, that's hot. So anyway, yeah, don't leave any chocolate in the car either, because that's going to melt. Unless your thing is melted chocolate. Ooh, that is pretty good. Anyway, sorry if I made you hungry. Alright, that was fun, you guys. We'll have more fun in the next section.